Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to talk about shear resistance of Glulam members for purposes of beam design. So, as I mentioned in the previous video, Glulam member shear design is quite a bit different than lumber member shear design. But like lumber, there are separate calculations for longitudinal shear and for notch shear, which we saw before. And the notch shear one for the tension side happens to be very similar to the notch shear for lumber. So that's one thing that is similar between the two. We'll touch on some other similarities as we go. The other difference in Glulam is that for notch design, there are two separate checks. One for if there's a compression side notch, which is usually the top of the beam notch, and a different one for tension side notch. We're going to explore how we calculate those different strengths. The compression side notch actually being a longitudinal shear resistance, another kind of longitudinal shear resistance, and the tension side notch being a fracture shear resistance like it was for lumber. So the first thing we're going to do, just like for lumber, is look at how we calculate the longitudinal shear resistance without consideration of notches. Okay, so when we're talking about longitudinal shear resistance for Glulam, outside of talking about notches, we have two options to calculate, and sometimes these options overlap, but sometimes it's necessary that we choose one or the other. And the way I'm calling these, this is just my way of calling them. They're not called this in the standard, but in the standard they're referred to as subclause B and subclause A. And I like to call these a simplified method and the detailed method. And you'll see the one on the left, the simplified method, looks very similar to what was the longitudinal shear resistance for lumber that we studied in the previous video. The only difference being that we use AG now instead of AN. The one on the right, the detailed method, is quite a bit different. And in fact, it's not even, it's a shear resistance, but it's not done in terms of shear force. It's done actually in terms of total force. And that's what W is. WR is a resistance to the total force on the beam. So if I had W along the length of the beam, a distributed load in kilonewtons per meter, then the total load would be W times L. And that is what I would check against this WR. So it's a bit of a funny way to do it. And I don't think you find this in other materials, this kind of approach, very typically. So we're going to compare these two methods and what they're used for, and then we will go through some of the details. So the one at the left, the simplified method, my check is basically that VR is greater than or equal VF, which is the shear at a location D from the support. So previously I had called that VF star. You can call it VF star. Basically, for the simplified method, we are allowed to do the same thing that we did for lumber, which is not consider that the loads within D of the support contribute to the shear for the purposes of calculating shear resistance. So I calculate my VR and I can compare it to VF at a location that's D away from the support. So that's the same as we had for lumber. And when can I use this simplified method? I can use it for beams as long as the volume of those beams, of that beam, is less than 2.0 meters cubed. Okay, so the other case that I can use it is for members that are not beams. So if I have a column that has some shear in it, so it's a beam column, then I can use this simplified method equation. Now for really big beams, I am not permitted to use this, and I will have to use the detailed method as we're going to see in a second. So those are the cases. Beams, small beams, but smallish beams basically with total volume of the beam less than 2 meters cubed, or members that are not beams. And again, as I mentioned, this is similar to the lumber equation, except we're using AG instead of AN. And what about the detailed method? Okay, well, my check for the detailed method is that WR must be greater than or equal to WF. And what's WF? It's the total factored load on the beam. So whatever loads I have, I add them all up and I find the total factored load in newtons, kilonewtons, something like that. And I compare that to my WR, which is my detailed method strength for shear, resistance to total load for shear. And when do I use this one? Okay, so I can use this on any beam, doesn't matter which size, but especially I need to use it for beams that have a large volume, a volume greater than 2.0 meters cubed. And I can use it for the smaller beams as well, but it turns out that it will be over conservative for those beams. So actually there is a benefit for small beams to using the simplified method instead of this detailed method. So you might ask, how do we consider that, the loading on the beam can be all different shapes and sizes? What's the difference between putting a uniform load on there versus having point loads, etc.? Like, how does it take into account what is the distribution of shear over the beam, since I'm just comparing total loads? Well, that's why we have this factor, the shear load coefficient, CV. And you can see that in the equation. So the equation has it has phi, so WR equals phi. FV is a strength, 0.48 is like a calibration factor, AG is my load, Z is my total volume in meters cubed, and CV is my shear load coefficient, and this is what accounts for the shape of the loading. Okay, so CV accounts for the shape of the loading. So depending on whether it's a point load or uniform load, or I have a series of point loads or whatever, depending on the situation, I get a different CV shear load coefficient, which is going to change my overall total factored load resistance, WR, for shear strength. And where do I get that? Well, there's a calculation method, which we're going to go over, but there are also some tables, which I will additionally show in a few moments when we look into CV in detail. There are some things which are common to both, which are our phi is 0.9, our capital FV, just like before, is small fv times our modification factors, KD, KH, KSV, KT, and our AG is our gross cross-sectional area. As per usual. Okay, so let's dive in a little deeper on how we get this parameter CV, because this is really the only difficult thing about this equation. Okay, so as we mentioned, there's two ways to get this shear load coefficient for calculating our total factored load resistance for shear WR. And the first way to do that is to use the tables. And this is what I'm calling the easy way, because it is definitely the easiest way to do this. And so the tables look something like this. Here's one. This is for a specific condition where I have a simple span beam. That means, simply supported. And I have equal loads equally and symmetrically placed. So if I have a load in the middle, if I have two loads basically at third points, if I have three loads at the quarter points, and a uniform load, then I can figure out the value of CV for this table. So, let's say, for example, I have a point load and a uniform load. So let's say I have a uniform load that is 10 kilonewtons per meter over 2 meters. So my total load from uniform loads is 20. Okay, and then let's say the point load is 10. Okay, so let's say I have a point load of 10, 10 kilonewtons per meter over the length. And so I have a total concentrated load of 10 and a total uniform load of 20 kilonewtons. So it's 10 kilonewtons per meter times 2 meters. Okay, then I can find my R, right? And my R, you see in the bottom left there, down this way, R is the total concentrated loads divided by the total uniform load. So in this case, I had 10 divided by 20, so my R is 0.5. So now for 0.5, I can say, okay, so I had one equal load, so I just have 1 point load, so therefore my CV is going to be 3.34. We'll do this a little bit more if we do an example of this. But this is just for one particular loading circumstance where we have concentrated loads that are equally spaced and then optionally a uniform load. If we don't have any uniform load in this table, then what would R be? Well, I would have a total concentrated loads basically divided by 0, which means that my R would definitely be 10 and over. So I would use this column here, depending on how many point loads I have. So if my loading condition doesn't satisfy this table, then I should go to another table. All right, here's a table showing what happens if I have basically a triangular trapezoidal type of load. So depending on what's P min over P max, so if this was triangular, then P min would be 0 and P max would be something, so then I would use a CV of 3.4. Okay, let's say that I had equal P min and P max, so I had a uniform load, then P min over P max is going to be 1, so my CV is going to be 3.69. Right? And here's some for cantilevers, here's some for distributed load here. Here is something where I have load over the center, and I have a P right at the center. So you can see that they're all specific loading cases. These are tapered beams, so this is like the size of the beam changes. And those are all the loading cases basically that are given in the standard that you can use to calculate CV easily. If it doesn't fit into one of these loading conditions from the tables, then you are out of luck as far as using the tables to calculate CV. You will have to calculate it doing the hard way, which is actually not that difficult, but it's just going to take a little bit of time. Okay, now let's say I have a triangular load and a point load. Can I then take part of the CV from here and part of the CV from here? Definitely not. Okay, so superposition does not apply. I cannot just combine two loading conditions from different tables to get some kind of average CV. Doesn't work that way. So if that is the case, then I will have to calculate it the hard way. Which, as I said, it's not like it's that hard. It's just not as easy as going to a table. So I'm just going to put a note about the superposition business. Okay, so as I mentioned, superposition doesn't apply. So I have to find a case in the tables that basically exactly matches all of the loads that are on the beam that I'm trying to design. So I can't just combine tables together. So if I can't find the exact loading condition in one of those tables, then I'm going to have to use the hard way, which means I'm going to have to actually do a calculation to figure out what CV is. That's not that bad. And I'm going to put out the method here step by step with an example as we go. So first step is find the shear force diagram. So I need to know the shear force diagram first, and then I'm going to use that actual shear force diagram to calculate what CV should be. So I'm going to show an example shear force diagram in a second. Okay, so the next step is that I'm going to take that shear force diagram, and here's an example shear force diagram. And I'm going to divide the length of that diagram into segments so that I don't have any sign changes and I don't have any abrupt changes. Now, one other thing to note is that when I am considering the value of the shear, I am disregarding the sign. So positive shears are going to be positive, negative shears are also going to be positive when I do the calculations that are to follow. But for now, I'm just going to divide this up. So abrupt change would be something like a change in slope, like here, sign change occurs here. Here there's a sign change. Here there's like an abrupt change in slope. Here there's a sign change, and this is the end. So that's the points that I'm going to use to divide up my member, and I will just take each of these segments basically separately, like this. So now I've divided it up into 6 different segments, and each segment is going to have an associated length of segment. Each length is called LA, and I'm just subscripting it with each number. LA5, LA6. And all of these segments can, of course, be different lengths. So it just depends on my particular shear diagram. So now that I have that, for each segment, I'm going to figure out basically what is the shear at each end, shear here, and shear at the center, right in the middle. And I'm going to do that for every single one of these. Okay, I'm going to delete those for now, just so it doesn't confuse the notes. I'm going to show it again in a second. So I'm going to find the shear force for each segment at the beginning of the segment, at the end of the segment, and right in the middle. And note well that these are all have to be in units of newtons, not kilonewtons. Otherwise, the calculation will not work properly. So let's look at the first segment from before as an example. Okay, so here's my first segment. And each of these points is one value of shear that I have to find. I can find those by calculating the shear by taking the area of the loading diagram, for example, to find the difference between the 2 points. This one is a bit tricky because it has parabolic shear distribution. But anyway, however I need to find the shear, I find the shear at those points, and notice that VC is the one that's in the middle. And this is segment number 1. So I would do this for every single segment, not just this one. Then the next step is I'm going to do a calculation to calculate this parameter G now for every segment. Okay, so I have the length of the segment times each of these shears to the power of 5, all added together. And notice that VC, which is the one in the middle, has a 4 multiplier as well. Remember that all of these V values are in newtons. So I'm going to get obviously a very big value for G once I take those Newton values and multiply and put them to the power of 5. And all of these values should be positive. So no matter which side of the shear force diagram these V's come from, all of those numbers should be positive. That'll make a difference, obviously, because it's a power of 5. Okay, so then my G's will also all be positive. Okay, and then once I have all of my G's, one for each segment, then I'm going to put them in a final calculation. And I'm just giving the one here that's for stationary loads. There is another one that is for moving loads, which I don't think we'll have use for in this course. So for stationary loads, that is loads that aren't moving, I can now calculate my CV, which, if you remember, is the whole thing that we're trying to do here, by doing 1.825 times WF times L, which is the total length of the beam, divided by the sum of the G values, all to the 0.2. So that that sigma is a sum. Okay, and you'll notice that the L's will cancel out. So the big L and the little LA that's in the G's, those will all cancel out. So the L's just basically have an effect of weighting the G's from each segment. And then we're going to multiply them by WF. WF is the total factored loads on the beam. WF is the factor that we're comparing to our WR, which is what we're trying to calculate here. And this is the sum of all G's. Okay, so that's it. So that's how you calculate CV. Once I have my CV, calculating it this way, or by using the tables, which is by far the easier way, then I'm going to come back to this equation for WR, and I'm going to sub my CV in there. And then I'm going to have my WR, and then I'm going to take my WR, and I'm going to compare it to my WF, which is the total factored load on the beam. Make sure that the total factored load resistance is greater than the total factored load applied. And that's how I do my longitudinal shear resistance check for Glulam. Okay, now we're going to need to talk about notches for Glulam. So how do I design Glulam for notches? Well, first thing that we're going to do is look at the geometry of notches for Glulam, because for tension side notches, it's quite a bit different than it was for lumber. Okay, so here are two different types of notch geometry that I can have for compression side notch for Glulam. I think the one on the left is something that you would be more likely to see. This is just kind of a taper at the end of the beam. Could be to accommodate some kind of roof geometry, could be for aesthetics. We still have a total beam depth D, and we have a notch depth DN. Same for both of these. We have a notch depth DN, calculated kind of the same way, just how much is cut out at the widest point of the notch. Okay, now we have to determine our E, our notch length. If you recall back to lumber, we define notch length as being between the center of the support and the re-entrant corner. This is not the case for compression side notches. We have a totally different notch length, and we call it something different too. So instead of calling it E, we call it EC. And it is defined as the distance between the inner edge of the support and the farthest edge of the notch. So instead of the re-entrant corner, it's the farthest part of the notch. So it looks like this. So this is quite a bit different than the previous E that we saw for lumber tension side notches. So I'm just going to make a note about that here. Okay, so EC is now from the inner edge of the closest support to the farthest edge of the notch, which is different than what we had for tension side notches in lumber, and indeed also for tension side notches in Glulam. So that's how I do compression side notch geometry. I just needed to have the definition of how I calculate EC for when we go to the equation. What about for a tension side notch? So for tension side notches, it's basically exactly the same geometry as for lumber tension side notches. So if you want to see a picture of what this looks like, refer back to the shear strength video for lumber. And again, E is defined as the length from the center of the support to the re-entrant corner of the notch. So re-entrant corners we talked about quite a bit previously. Okay, so now we're just going to look at how do we, now that we know the geometry of the notches and we know how to define E and DN and D, how do we actually calculate the strength of these notched members for compression side notches and tension side notches? Okay, so for compression side notches, we have to first look at what is the notch length relative to the depth of the beam. So that gives us an indication of the kind of the relative length of the notch. And this is one place where there is a slight difference between 08614 and 086 from 2019. And I'm going to point that out here. It's a minor difference. And we're going to see it right now. So there's two different criteria. One for when basically the length of the notch is greater than the depth of the beam, and one where the length of the notch is less than the depth of the beam. So for the first one, for length of the notch greater than the depth of the beam, that's the criteria in 08614. For 08619, they changed it so that it's greater than the depth of the beam minus the depth of the notch. So it's the remaining depth of the beam that's used. So that's a kind of minor difference. Okay, and for that, we're going to use this equation. VR is phi, capital FV, times 2AN divided by 3, which you will recognize is the notch strength equation from lumber. And AN, obviously here, does not include the notch. So the notch is cut out of AN. So AN is the kind of minimum net cross section after you cut out the notch. So that is if I have basically a really long notch cut out, then I'm going to have to use the AN. Now, if I have a shorter notch cutout, again, I have slightly differing criteria. So it's similar if EC is less than D, the depth for 08614, or less than the depth minus the notch depth for 08619, then I'm going to use this more complicated equation, which basically has kind of an interpolation parameter built in. So I still have phi FV, I still have 2/3 this time AG, and then I have 1 minus notch depth times notch length divided by total depth times total depth minus notch depth. Okay, so this interpolation parameter basically brings it from if I had a 0 length, then the right term would just equal 1, and I would have basically phi FV 2AG over 3. And then if my length was D minus DN, then I would have on the right side basically exactly, I would be subtracting DN over D, which would give me my AN. You can convince yourself of that. Like, look at when you have D minus DN, and you can kind of see why this was changed, because for 2019, because before the change, basically this interpolation was not continuous, whereas now it is. So otherwise there would be a slight discontinuity when you went from one side of D to the other side of D and used the two different equations. It didn't really totally make sense. So this is a good change that makes this equation make sense now. And so it gives a transitional strength basically between using AN and AG. Okay, so what do these look like? Let's just draw them out quick, what you would kind of expect. Short notch length versus long notch length. Okay, so for the one on the left, we have a long notch. This is our EC. It has to be greater than D or greater than D minus DN, depending on which version of the standard you're using. And on the right side here, we have a shorter EC where we have less than D or less than D minus DN, depending on which standard you're using. So that's a short notch versus a long notch. We went over the definition of EC. What happens when EC equals 0? What does it look like? If EC equals 0, so if EC equals 0, that means that the notch lines up directly with the edge of the support, the inward edge of the support. And in this case, there is basically no reduction for notch shear because the section at the support is the full section. So there's no reduction. Okay. Otherwise, you know, you can see that for the one in A, over the support, like at this section, we are cutting a lot of the member out. So that's why for EC greater than D, we're going to use AN, because basically we're reduced to the total net section, but we're actually using this section. Okay. Well, I mean, I guess we can use the second. We can use the section right there, I think. And then on the right, you know, as our EC reduces, we interpolate between using the net section and the gross section, because this line is moving up and up and up. Like this point here is moving up and up and up as EC reduces. Okay. So the last one is the fracture shear resistance for tension side notch in Glulam. So this was compression side notch. Now let's look at tension side notch. Okay, so for fracture shear resistance on the tension side for Glulam, the equation is basically identical to the fracture shear resistance for tension side notches in lumber that we looked at in the previous video. The difference is that FF is calculated differently. So small FF for lumber was just 0.5 MPa all the time, no matter what kind of material that we were using. Here, FF is a calculation, which is a maximum of two different potential factors. One is 2.5 times B effective to the power of negative 0.2, and the other is 0.9 MPa. So I calculate both of these and I find out which one is greater, and that's the one that I use. Okay, and B effective is calculated like this. Okay, B effective is the lamination width for the Glulam. And we know that sometimes we get Glulam pieces that look like this, where basically we have one lamination goes across the entire length. Sometimes it looks like the one on the left there, where the laminations don't go across the entire length. And in that case, we're going to take the width of one of the laminations. So this would be B effective for this case. And for a Glulam that has only one lamination, it's just going to be basically the width of the piece of Glulam overall. Now, Kn in that equation is the same as it was before. It's just the notch factor, and the calculation is the same, but I'm going to put it in here for completeness. That's the equation for Kn that we saw before. This complicated equation with alpha and a eta, and it includes the notch length E and the depth of the notch dn. And if I do this calculation, I get my Kn, or I can use the tables like we mentioned before, which are in chapter 6 and look like this. And I can calculate my alpha and I can calculate my eta. And based on that, I can find Kn square root of D in this table. And then if I take that value and divide it by the square root of D, the depth of the member, then I'm going to get my Kn that I can use in my equation. And so that's it for shear design of lumber and Glulam. So now we've totally covered Glulam. And at this point in the videos, we have basically everything that we need to design any beam. And so it's time to be able to look at some examples.